This week, I will introduce to you Pascal's Triangle, a fairly simple yet mathematically rich concept. First, let's look at how to build Pascal's Triangle. At the top center of your paper, write the number 1. On the next row, write 2 1s, forming a triangle. Every row from here on out will start and end with a 1. The interior of each row will be determined by summing the 2 numbers above it. Continue this pattern for the desired number of rows. Now that we've built Pascal's Triangle, let's look at some of the secrets it holds. To make the hidden sequences easier to see, left justify the triangle, meaning move everything to the left. What do you see? In the first column, it's all 1s. In the second column, it's the natural numbers or counting numbers. In the third column, it's the triangular numbers. These can be thought of as the number of dots needed to make varying sizes of triangles. Similarly, the fourth column is the tetrahedral numbers, or triangular pyramidal numbers. These can be thought of as the number of dots needed to make the pyramids with triangle bases. The next column is the 5 simplex numbers, followed by the 6 simplex numbers, and so on. If we take each row and take the sum of the terms in that row, the resulting number is a power of 2, starting with 2 to the 0. If you take each row and squish the terms together, the triangle reveals the powers of 11. This works very easily for the first 5 rows. When you get to rows with double digits, you carry the tens place over to the number on its left. The perfect squares of the natural numbers in the second column can be located by summing the number to the right with the number below the number to the right. For example, 2 to the second power is 1 plus 3 equaling 4, 3 to the second power is 3 plus 6 equaling 9, and 4 to the second power is 6 plus 10 equals 16, and so on. To find the numbers of the Fibonacci sequence, a sequence derived by adding the previous 2 numbers to get the next number in the sequence, sum the diagonals of the left justified Pascal's triangle from earlier. By doing that, we get 1, 1, 2, 3, 5, 8, 13, etc. The Pinsky triangle is a famous fractal involving triangles. By shading in all the odd numbers of the original orientation of Pascal's triangle, you'll get a picture that looks similar to the Sierpinski triangle. Let's recall the combinatorics formula n choose k. In Pascal's triangle, let n be the row number and k be the entry in that row when counting from 0. So if you want to calculate 4 choose 2, look at the 5th row, 3rd entry. You'll find the answer is 6. Suppose you have the binomial x plus y, and you want to expand it to the power of 2 or 3. One method is to use the distributive property and multiply out each term and then combine like terms. By using Pascal's triangle, you can just skip to the answer with no multiplication. For example, let's expand x plus y to the 3rd power. We would use the values of the 4th row, since the first row is raised to the 0 power, and the entries of the 4th row in Pascal's triangle will be the coefficients of the expansion. Then you fill in the x and y terms as outlined in the picture. We can generalize the idea from expanding binomials with Pascal's triangle into a more usable form. This is called the Binomial Theorem. Let's try 2x minus 3 to the 3rd power to see how the Binomial Theorem is used. X equals 2x, y equals negative 3, n equals 3, and k is the integers from 0 to 3. Next, we must fill in the values for k, and since k has 4 different numbers, we will have 4 different versions. Then simplify, starting with exponents of 0 or 1 first, then compute the rest of the exponents. We already know the combinatorial numbers come from Pascal's triangle, so we just need to look them up. Then finish multiplying and simplifying. The binomial distribution describes a probability distribution based on experiments that have 2 possible outcomes, like tossing a coin. Let's say we're interested in tossing heads. We'll call this a success with probability p. Then, tossing tails is the failure case and has the complement probability of 1 minus p. If we design an experiment with 3 trials, or 3 coin tosses, and want to know the likelihood of tossing heads, we can use the probability mass function for the binomial distribution, where n is the number of trials and k is the number of successes. As you can see, the formula is very similar to the binomial theorem, except there's no summation, and we have p's and 1 minus p's. If we assume the success probability for tossing a head is 0.5 or 50%, then let's calculate the probability of flipping heads 0, 1, 2, or 3 times. Fill in the equation for n equals 3 and k equaling 0, 1, 2, and 3, and complete the computations. As it turns out, the likelihood of flipping 0 or 3 heads is 12.5%, and the likelihood of flipping 1 or 2 heads is 37.5%. Pascal's triangle holds a lot of interesting secrets. Which ones were new to you? Which ones did you already know? Let me know in the comments of the video or email me. I'll see you next week.